Okay. You can start, Tom.
Okay, so let's start.
Yes.
Okay, hello everyone. I'm Tom from Simon Fraser University. I'm currently a master's student here doing research in data mining and probably some machine learning. And today my topic is a brief introduction to deep learning. It is very brief because it's a very large topic, and I don't think anybody can cover everything of deep learning in 30 minutes. So it is a very natural question. What is deep learning? First of all, it's a family of machine learning models. And it's a supervised learning model. So we take some data with a label, and we train the model to learn the relationship between the data and the label. Sometimes we do classification, or sometimes we do regression or other missions. And the structure of the model usually, or mainly, is neural networks. And today we can only introduce a very basic version of these neural networks. And it's very popular now. It's popular because it has some extraordinary achievements. And first of all, before we introduce the details of the model, we can have a glimpse of what are these achievements. So I'll just introduce three main achievements and interesting achievements here. And some of them happened just recently. Okay, first is image understanding. Like just 10 years ago, I believe 10 years ago, the scientists and researchers are still struggling with teaching a computer to learn what is in an image and what are the object in the image. Say if I give you a photo of a mountain, does a computer recognize that it is a mountain? But now, so currently, I think this is a result of research in last year. It's now a computer with deep learning can do the following things. So look at a very leftmost column here. So the upper left corner, this is a photo, and the program described it as a person riding a motorcycle on a dirt road. So this sentence is generated by a deep learning model, or actually two deep learning models. First, it understands what is in the image, and second, it uses another deep learning model to generate a sentence describing the content in the image. And next one is a group of young people playing a game of frisbee. And next one is a herd of elephants walking across a dry grass field. So this column represents those results described without errors. And this column, second column, means described with minor errors. And the third column means somewhat related to image, and the last column means is unrelated to the image. So this is a screenshot I took from the original paper, and but we can see that this is the most recent result, and it's going to be better. And we can see for those
Slide doesn't change here.
Sorry, what?
The slide doesn't change from here.
Oh, really? I'll wait a sec. I'll do that one more time.
Okay.
Can you see that now?
Yes, now it's perfect. Thank you.
Okay, yeah. I'll go through this image understanding again.
Okay.
So the first column here, we can see it's a person riding a motorcycle on a dirt road. We can see from the image that it is a person riding a motorcycle on a dirt road. As this column is a perfect result of using a deep learning model to describe an image. And other columns, they have somewhat relationships to the image, or it's unrelated to the image. But I believe it's going to be developed to a better stage that the description of the plot is acceptable for human beings to understand. So compared to 10 years ago, that the scientists are still struggling to identify what is in the image. This is developed rapidly, and thanks to deep learning, we can do that at a fast step. And I believe that it's gonna be there are gonna be more results in this specific field in this year or next year. And the another one is the self-driving car. This is from Google, and there are several points to solve before you can make a self-driving car. First is environment recognition. So when we're driving, we have to read the traffic condition. We have to know the traffic signals. We have to understand the cars and pedestrians around us, and we have to say recognize if that is a crossroad, if I can turn left or right, or where should I turn. And we have to make real-time decision, say when should I brake or when should I speed up, and where can I park my car. And next one is cooperation. We cannot make a robot to mimic a human being driver to drive the car. We just have an operating system inside the car, and it can operate the car electronically. In this whole product, deep learning, I think, works in the first point, which is the environment recognition. It recognizes, say, well, we can see from the plot, at the head of this car, it has a black bar here. I believe it's a sensor, probably a camera, or both a sensor. It captures the plot in front of it, and on top of it, it's also maybe a combination of several cameras or several sensors. So it's a huge sensor site. So it not only captures images, of course, it captures sounds. And the car has to get a model to understand all these input. So here's where deep learning makes it work. And for the latter two part, they're from another system, I guess. But here, the first step is solved by deep learning. I believe deep learning can do that. And third example is a system which plays the game of Go called AlphaGo. So the game of Go is a really simple board game played on 19 by 19 chessboard. It's the chess-like game that two players play black stone and white stone alternatively on the board. Every time they can only play one stone, and their goal is to capture as much area as possible. And so they have to calculate each step's value and how to beat another player. So almost 20 years ago, there's a machine developed by IBM called Deep Blue, which beat the world champion at that time, Kasparov. And that is like a start of using artificial intelligence to beat human being in some specific area. But it's almost 20 years later that we have another machine beat the human best player, Lee Sedol, in this area. Lee Sedol was treated as the best player in the last 10 years because he's got the most championships in the last 10 years in this field. And the difficulty of developing such a system is in the game of Go, each step or each move, there are so many possibilities. Say if on an entirely empty board, we have 19 by 19, that is 361 possibilities to take a move. And the following move has 360, and the third move has 359 possibilities. So we can see that only three moves, they're actually 361 times 316 times 359. That's almost over 1 million. That's actually already over 1 million possibilities. And every game, there are more than 100 plays. So the computer needs to have some strategy to reduce the space it needs to search in order to find a valid move and a good enough move. So here, where the deep learning model takes charge of is there are two different types of network here. The first type of network is to evaluate the current board to have a guess of the winning rate of the black player and white player. So the input is just the image of this board, which is, yeah, you can think it as a 19 by 19 plot. It's an image, and each a stone is like a pixel on the image, and it can be trained to produce a winning rate for black player and white player. And another model is to predict what is the best next move. So on this 19 by 19 image input, it has a guess on the probability that the next move is going to be taken on each empty cell, so that deep learning is used to reduce the possible moves on the board. So at the first move, the candidates is not 361 moves together, but probably just 5 moves or 10 moves or no more than 20 moves, so that people can search to a certain depth and improve the power of play. So it has a smart brain to guide the system where to move and where is likely to be a better move, where is unlikely to be a better move. So we don't have to look into those unlikely good positions. So this is a key point that AlphaGo won. Okay, so these three are three achievements that the AlphaGo, that the deep learning model has achieved, and there are a lot many. So next we can take a look at the details of the model. Before we directly go into the deep learning model, we first look at a simple shallow learning model. And this is a neural network. We can see on the right side of it, there are 3 layers, and the first layer here is marked as blue circles. These layer takes in the input values, x1, x2, x3. There are 3 numbers from the training data, and +1 here, this is a bias node. And this is layer 2, we call it hidden layer. And this is layer 3, we call it output layer. It generates an output where we get a prediction from. The prediction, we want the prediction to be as close as possible to the true label in the training data. So the reason we call this layer 2 as the hidden layer is we know that layer 1 is the input and layer 3 is the output, and hidden layer is something hidden from us at the beginning, so we call it a hidden layer. And there's one important thing in this structure is this the arrow. The arrow pointing from one layer to the next layer, one node on the first layer to another node to the next layer. They represent a weight. It's a number. So say from the top node here on the hidden layer, in the hidden layer, we can see that there are 4 arrows pointing at it. So actually, it is we can see that the values are w times x1, the w on this arrow, which is the weight times x1, plus the on this arrow, the weight on this arrow times x2, and blah blah blah. There are 4 terms here. It is a weighted sum of all the values on this layer. But we want to, but if there's just if just the weighted sum is a linear combination, so usually a linear combination does not capture the powerful enough features. So we add a nonlinear activation function here. So here is the f. And here on the left side of this slide, we can see this formula. This formula describes, or you can say it's a projection from a first layer to the next layer, this layer to the next layer. That for this node, we have the weighted sum of all the values from the previous layer plus and put it into a nonlinear transformation. We will talk about why we want a nonlinear transformation later on the next slide. And for this node as well, but the weight may be different. And for this node as well, the weights may be different. And this holds between layers. So from the hidden layer to the output layer, we also have these weighted sum in an activation function. The activation function is a nonlinear transformation. So we can see if we put, at first we can see how it predicts. We put the input x1, x2, x3, the three numbers here. And as suppose we have a trained model, so the weights are fixed. We can calculate it. We can calculate the values on the hidden layer by these relationship f here. We can get the value on the hidden layer, and we predict from the hidden layer to the output layer. Then we can get the prediction from the output layer. So it's a feed-forward neural network. It's a feed-forward process. So we from the layer 1 to layer 2 to layer 3. It's straightforward. Okay, so it's important to understand why we need a hidden layer here and why we need a nonlinear transformation between two layers. So it's broadly accepted that a hidden layer, the values on the hidden layer is actually a description. Is describing some patterns, or we call it features, from the input. Let me give you an example. So we have, say for the three inputs, we have is three numbers of a person, where the three numbers are his monthly income and his daily cost, and maybe his age. Yeah, so these three numbers, and we want to predict if he can buy a super good car, say maybe a Ferrari car, and these are the income and his age. And sometimes we think his income, monthly income, is important. Of course, it's important, but what if his daily cost is very high, that he does not have enough money to buy the car? So maybe we want to extract something like the monthly or his daily cost and his daily the money he saved daily and the money he can save monthly or yearly. And so the hidden layer could have the possibility to capture things like that, so that the hidden layer has a higher level of understanding of the input feature. Because we have a prediction goal, we want to know more from the input. The input information is limited, but if we make we do some calculation, we can get some higher features or characteristics of the input feature. So the hidden layer here is working as a description of the input layer. So with these better understanding or the better characteristics, we can make the output, we can make the prediction more precisely. And the reason why we use the nonlinear transformation is sometimes the interactions among all the dimensions of the input data, say x1, x2, x3, probably they work in a nonlinear way. Probably there's a pattern. We can find a pattern, say x1 times x2 and over x3, things like that. We don't know, but it's possible. So a nonlinear combination can gives us way more information than a linear combination. So this is the intuition of building a model like that. And we now know how to predict with the neural network. Now it is the main training program. It is a basic training program, and it's very useful. It's called backpropagation. So I can introduce the workflow for you, but I'm not going to touch the formulas here. So first, we know how it predicts. So let's predict it we can generate a predicted value y hat here. Then we compare it with the true y. Now we know the difference between the predicted value y hat and the true value y. So what we want to do is to train the model to reduce the difference. So we modify the weight here from the hidden layer to the output layer to reduce the error. But this is not the only place that generates the error. But also this part of weight, where it's from between the first layer to the and the hidden layer, this part also contains a lot of weights. And if they're not generated carefully, they will also generate errors here. So we get a difference, we modify the weights between the hidden layer and the output layer, and there are some remaining errors. And then we modify the weights between the first layer and the hidden layer to correct the remained error. So we call it this process as back propagation. Means we're starting from the output and we go backward again, take a step back to the weights on between the hidden layer and output layer, and we take another step back to the weights between the first layer and the hidden layer, and we modify them. So it's a back propagation. We propagate the error from the output node to the hidden node to the first input node. So we call it back propagation. So this is the training step. Now we have a very brief understanding of a shallow learning neural network. So it sounds really easy that we can just add more hidden layers to get a deep learning model. Actually, the deep learning model, the deep in deep learning means there are so many hidden layers, makes it deep. A good thing about having more than one hidden layer is sometimes we may want more layers than to extract the features. Say if we have an input as an image, have an image as an input, maybe it's probably that the first hidden layer extracts those straight lines or those curves. We know where we have a line. And the second hidden layer could combine those lines to see. So there we have a square. On the upper left corner, we have a circle, things like that. So it's a higher level understanding. And maybe the third level, they can have another understanding based on the previous result. So the more layer we have at a moderate level, the more layer we have, or the better, or the more abstraction we have about the input. So probably it's going to help our prediction. So sometimes people want to add more hidden layers here. This sounds pretty good. We can just use the backpropagation model as we propagate the error from the output layer to the second hidden layer and back to the first hidden layer and back to the input layer. But actually, we have a problem here. There are three main difficulties here. The first is, as we introduce more hidden layer, we have more weights connecting the two layers. So we have more parameters. The weights here are called parameters because we have to learn it from the data. That means we have to use a lot of data to train it, because the more parameters we have, the more data we need to make an accurate estimation. But the thing is, probably we have a lot of data, but most of them probably are not labeled. If they're not labeled, we cannot use them to train a neural network, because we want to have a true label y in the backpropagation process to know the difference. If we don't know the difference between our predicted value and the true value, we don't know which direction we have to go when we are modifying the weights. So this is the this is the first difficulty, not enough labeled data. And the second is local optima. And this is a term in when we are trying to optimize a very complex function. And because as the layers increases, we have more parameters to initialize. The first, we have to initialize them with some random number, some small random number. But it's likely that we will fall into some local optima, which means it's not that ideal, but maybe we cannot optimize it too much. It has an obvious limit. And the more parameters we have, the more complex the problem is, the more likely we're going to fall into a local optima. Thus, we're not going to get a satisfying result. And the third one is called diffusion of gradients. So we come back to the back propagation. When we perform our second modification, we modify the weights based on the remaining errors. If we have more hidden layers than one, the remaining error is going to be smaller and smaller as each time we step back to the previous layer. So if we reach to the weights between the input layer and the first hidden layer, the remaining error might be really, really small, that we can only change our weights by a little step. So that's really very inefficient. Probably we have adjusted the weights between the last hidden layer and the output to a very satisfying level, but we don't have a really good abstraction at the first level. That is not helping our performance as well. So these three are the difficulties if we just follow the usual backpropagation and we just add the hidden layers. So next, the current deep learning model solve this problem beautifully by a model called autoencoder. We first look at the plot on the right side of the slide. We can see that it is a neural network, but with much more errors. It is actually a neural network which is focusing on recovering the input values from the hidden layer. The intuition of this goal is very simple. We want the hidden layer to be a description of the input. So how's the quality of the description? The description might be just some rubbish if we are not training it to a satisfying level. But if we can recover the input from the hidden layer, that means the hidden layer contains almost the same information as the input. And this means the hidden layer has almost no loss of information. It is a good it is representing the input in a very high quality level. So we trust the hidden layers result. And when we are training this thing, one good point is we don't need a labeled data. The unlabeled data has no true label, has no Y. But here we need no Y, we just need the X here. Where is the input data? We have a lot of unlabeled data. We can just train the autoencoder, and we know how to describe the input values pretty good by an autoencoder. So in this way, we have tackled the first problem, which is not enough unlabeled data. And how do we make it deep? Here's a simple idea. It's called stacked autoencoder. So here are three different neural networks. The first is similar to the one we have in the previous page. That is, we take the input in, and we use a hidden layer to learn some higher level characteristics of the input, and we try to recover the input again. And next, we use the hidden layer in the first autoencoder as the input of the second autoencoder, so that we can train another level of abstraction or another level of description with the second hidden layer. We can see from the bottom here, the first neural network has input features 1 and output. And the second neural network has the input as the feature 1. Next we have the feature 2. And we have the output also focusing on recovering the input of this autoencoder. And lastly, we extract the feature 2 from the second autoencoder. We connect it with an output node, output layer. So we can make predictions on this second feature. If we compress these three plots into one, we get something like that. The input, feature 1, and feature 2, and the output layer. So the feature 1 is trained from autoencoder. Feature 2 is trained from another autoencoder. And then together, we now have a neural network. Lastly, we call it fine-tune at last step, which is we use this backpropagation algorithm to tune the weights here in this whole network to make it work better. So here are the reasons why a stacked autoencoder solved the previous problems. The first problem is we have not enough label data, but autoencoder does not need labels to get some descriptions of the input. And the local optima is we have this stacked autoencoder, we call it pre-train. We initialize with some high quality hidden layers. So because we believe it's high quality because it can recover it, so there's no information loss. We believe it's high quality, so it usually gets a better result because the feature 1 and feature 2 here contains almost the entire information of our input. And we avoid training entirely at first. We train the weights, the green weights, the red weights, the yellow weights separately, so there's no diffusion of gradients. We have trained them to a satisfying step, so they are meaningful. They're not inefficiently tuning every step we do backpropagation. So this stacked autoencoder model solve the problem, and we can make the model deeper. And of course, you can have feature 3, 4, 5 as you like. If you have enough data and you believe that your data needs that much layer of description. So here is a very simple deep learning model. And the idea is I think this idea is the simplest among the whole family of the models. There are other, we can call it subfamilies of models. This is convolutional neural network, and this is recurrent neural network, and this is long-term, short-term memory neural network. The convolutional neural network is mainly used to recognize things in image and to take images and inputs and generate some predictions. And the RNN, actually LSTM, the long-term short-term memory neural network, is a sub-version of the recurrent neural network. It takes in a sequence of data. Say usually we have in the natural language text, say a book, the words, they have a natural order in it. So the RNN knows how to deal with those ordered input, and it can extract some more meaningful information based on their order. And there are a lot more families. And here are some R packages that can do deep learning. First is called MXNet. It's developed by the organization called the MLC. And I am also a developer of this package. And the next talk will be introducing this package. And there's another one called H2O. It's a whole library for machine learning, and it's not only focusing on the machine learning, on deep learning models, but it has the function and it has a really good R interface. I encourage you to try both of these things and compare if you to see if you like any of them. And here are some reading resources. Most of my plots in my slides, I use them from a tutorial called UFLDL from Stanford, which is short for unsupervised feature learning and deep learning. And this is written by the famous Andrew Ng from Stanford. This is a really good tutorial. You can learn more on that in this tutorial. And there's another website called deeplearning.net. And in these two, on these two websites, they have some instructions for users to implement their own deep learning model. Say UFLDL, they teach the users to learn deep learning by MATLAB. And the next one teaches users to learn deep learning by Python. And the last thing is, of course, research papers. This field is being researched rapidly, and every year or even every month there are new things coming out. So if you're really interested in it, after you finish some tutorials, I highly encourage you to follow some research papers. Okay, so that's my talk, and I'd like to answer any questions you have.
Thank you. Thank you very much. It's a very good introduction of just the idea of deep learning. I'm not very familiar with deep learning, so everything I still can't fully understand. A very basic question. Does it mean deep learning just actually it's deeper version of neural network, not deep learning? Do we have like deep learning for other machine learning methods or just neural network?
Yes, as far as I know, of course, I'm not a researcher in this field, but as far as I know, there are some other things having similar structures. So they have connections, they have nodes, but they're not trained as neural networks. Say, there's a name called restricted Boltzmann machine,
Okay.
which has nodes. It's more like a probabilistic graphical model. It has nodes, has connections, and it also has hidden layers and visible layers, but it's not trained by the backpropagation algorithm. And the loss function there is different. They share the similar topological structure, but actually the underlying theory is more or less different. But mainly, as far as I know, I think now people just use neural network to train deep learning models because deep here is above hidden layer.
Okay. For the autoencoder, I understand it as an unsupervised model. And I don't know how to, there are some unsupervised model like clustering model, but there's some rule that you can train them. I don't see that rule. What rule you use to train those X to be next layer?
Rules here?
Rule means like for cluster, you want samples or observations within the same group to be as similar as possible.
Oh,
and
I see.
samples.
So here in autoencoder, the rules here is the output. We want the output to be as similar as input as possible. So we want the output to be, or in a perfect prediction, the output is exactly the same as the input.
The output is what? The output is your response variable?
Yes, we output. Okay. In the output, we want to recover the input. If output is exactly the same as input, then the feature contains all the information that the input has.
Okay.
So that's
and
the
then
situation.
What you use is the hidden feature, the one you get instead of the output, right?
Yeah, what I want to use is the features because they are another level of description of the input layer, while it keeps all the information of the input.
Okay, can I understand it as like PCA, you find new components
Yeah,
instead
you
of
can understand like that. They are
okay,
similar.
okay, that's awesome. Thank you. Then
Right.
we will move to Qian. You will talk about the package MXNet.
Yeah. So can you hear me?
Yes, we can
Yeah.
hear you perfectly. You should share your screen.
Okay, okay, let me see how to
Oh, and if you have any question, right now you can't talk through here, but you can leave your question under the event page. I know there are some viewers online. And I will upload Tom's slides later. You should be able to see Chan's slide already. Okay, Chan, you can start. We can see your slide.
just to make sure it works well, right?
Yep.
Okay. Okay. Okay, it is a pleasure to give a very brief introduction about the MXNet. Theoretically, this presentation should end in 20 minutes, and actually I do not have enough content to show in this presentation. And first, an introduction to myself, and you can call me KK. And if you read Chinese, this is my Chinese name. I'm a PhD student in mass spectrometry from Indiana University. We are some very the old style bioinformatics research. Right now we are still working on some like sequence alignment or maybe the speckle alignment. Basically, I am a C++ and R developer. I'm part of the RCPP team, and if you have any questions about the MXNet, you can find more info from the following links. And so let's start with the very simple question: what is the MXNet? Okay, first we know there are many deep learning platforms, and just as He told you, in the R you can use the MXNet, or you can use the H2O. Since this summer I will work in the H2O, so no matter which one you are using, you will use some code from me. And there are so many deep learning platforms using the GPU, and we can see that the Cyano, the deep learning.net, the tutorial is basically the usage of Cyano library. And of course, I think many people has heard about the TensorFlow from Google. And we can see the MXNet is here. The team leader, Tianqi, is from University of Washington, and Li Mu is from CMU. And I can give you a very brief idea about what is the MXNet. You can think it is just a deep learning library, but so is there any special about this library? Personally, I think the most special point is about is that the MXNet is portable. What I mean portable is the MXNet. It can run on many different operating systems. No matter you are using Linux, you are using Windows, or you are trying to run the MXNet on your mobile device, and it can be used as the backend for many scripting languages like the R, like the Julia. So the other question is why MXNet? Since we already have so many deep learning platforms. And the first reason, personally, I think we are the only one has the R interface. So this is a very good reason for many R users to use the MXNet. And then why not TensorFlow? Why not spend some time to provide an R interface for the TensorFlow. Especially, Google has released the machine learning cloud today. So we have many good reasons to use the TensorFlow. First reason is from our benchmarking, TensorFlow is not efficient. We can see the result. MXNet or Caffe or Chalk, we are much better than the TensorFlow. And the second question is, we can have the Windows support using the MXNet. And if you really pay attention to the TensorFlow code on the GitHub, I think you already know that you can never, at least you can not use the TensorFlow on Windows right now. Maybe in the future, but right now you can use the R interface and you can use any part of the MXNet on Windows. And actually, there is a personal reason that I do not want to spend time on the R interface for TensorFlow. Google has rejected my internship application. So basically, I just do not want to spend any time on the TensorFlow. And if you want to try the MXNet for the Windows and the Mac user, it is very simple. You can just use just 3 lines of code, and we will update our package mostly every 2 weeks, but it depends. But we will try to let you can install the R package easily. But if you are using Linux or you want to use the GPU backend, you need to compile by yourself. And a very small demo. Actually, I really do not like this demo because everyone uses this demo. Okay, you can get the data set from Kaggle. This is I think this is the first Kaggle competition everyone will try. And what I want to show in this demo is I want you to learn about the basic syntax of MXNet. You can just read the data, do some normalization, and you can build the neural network 1 layer by 1 layer. We have the input, and then we have a fully connected layer, and we have an activation function, and we have another one. You can just build the network layer by layer. And after you build the network, you can just run the network and pay a little attention to this parameter, the context. Right now, we are using the GPU machine to run the neural network. And I want to confirm you that the R is using the GPU. It is not only run the CPU machine, and it is really fast. And then let's try the very little shiny app.
Can you explain a little more what is GPU? I don't think everyone knows. I heard about it. Is that a parallel computing stuff?
Yeah. You can think it is a new hardware that it is really good for the parallel computing, and especially very good for the neural network training part.
Okay. Thank you.
And actually, if I think you can find some benchmarking on the online using the GPU machine. It is really faster than the CPU machine. And let's try a very simple shiny app. I think many of you maybe has already know this app if you read the R bloggers. And it is. I just want to show you that with all the models you have learned about deep learning, and then you can read a figure and let the network tell you what is inside the figure. And this Shiny app is using the Inception BN model, and actually it is quite a complicated model. If you really want to train the model by yourself, you can just as I have said, you can build one by one layer and build the model and train the model by yourself. But I think most people do not want to spend that time. So in this Shiny app, we just download the model file from over the internet, and we load the model and we use the model. And we can just from the code, we read the model, we load the model using MXNet, and we read the image. And we do some pre-processing for the image, and we just do the prediction. And actually, right now, over the internet, you can find many good deep learning models, and you can just use it. At least for the image classification, it is really good. And you can think this one is around 20. It is in 1998, and we can say it is quite simple. But from now, the neural network, it is become more and more complicated, and we can have more and more. We can have better and better results, but we need more powerful machine, and that is why many people are trying to use the GPU to training the deep neural networks. And you can just find the source code on the GitHub and run the Shiny app by yourself. It is quite easy.
And how about the dog? Does it tell you the dog? Can you go back to the picture? Oh, this one.
No, actually, the first one, it is still a kind of a dog.
So what the computer tells you?
Yeah, this is the result from the.
Oh, that's the result. Okay. Oh,
let's try another image. Maybe you can see some words.
That doesn't make sense to me. That result doesn't make sense to me. I don't know what it says. Is that English? Oh. Okay. Wow, that's cool. That's a kind of dog.
No, the second one, actually, I think all the results are different kinds of dogs.
Oh. Okay. So what the algorithm did is it searched online to match.
It is training using the whole MXNet dataset from Stanford University, from the Professor Fei Li, and it is a model trained by many images. So right now, you give me a new image, I will do some prediction, and I try to tell you what is inside this new image.
Have you tried to use your photo?
Okay, I think I do not have a photo by myself, but okay, you can just give me any keywords we can search and try.
Okay, never mind.
Okay, maybe. Okay, actually, we have a blog about this. And personally, I think this result is quite good. This is a photo I took in Seattle, and you can see.
What does it say?
The mountain tent. The breakwater. Okay, where is the motorboat? Okay, maybe on the water. And you can see there are many umbrellas.
Okay, that's cool.
You can try. It is okay. Maybe let's just use some image. Just let's try a small cat. Yeah.
Oh, tiger cat,
Yeah.
Egyptian cat, adorable.
Actually, I don't know which kind of cat.
I don't know either. Thank you.
And so I guess to show you two very simple demos about using the MXNet. So in the first one, I show you a very simple example about training a model by yourself. You can just build the neural network one layer by one layer and one layer. Actually, if you really want to try, you can try some really complicated neural network. And if you build it successfully and done the training, actually you can just share the model file with us. It will save us very much time. And another one is a Shiny app. Actually, the most important part is you can share your model file with other people, and they just load the model and use the model. And okay, thanks to all the university and the companies that support the main developers of the MXNet. And well, thank you for your time. So do you have any other questions?
No, so far we don't see any question for you, but I see a question for Tom. Tom, are you still there?
Yes, I am here.
The question is, how do you address regularization, especially when you have more weights?
I'm sorry, can you repeat that again? I can't hear you
I
clearly.
sent it to the group chat. You can see it.
Okay.
But the question is, how do you address regularization, especially when you have more weights?
Oh, there's one scenario where we say for the hidden layers we have more nodes than we have in input. Say we have 1,000 dimensional input data, but sometimes we also want to have, say, 1 million hidden nodes in the hidden layer. So this is one scenario where we can have a lot of weight. So yes, we can use regularization to solve that, whereas we add some regularizations there to make the weight sparse, so that there's only limited nodes in the hidden layer that can be, or we say that can be activated, where it means it can be have some large enough values that is not zero. Usually we do regularization in the loss function, so that when we are doing backpropagation, we have the regularized penalty also propagated to the previous layers of the weights, so that we can also penalize the weight by the regularization. So I'm not sure if that answers the question.
Yeah, so far I can't talk to the audience.
Yeah, so if there are more questions, I can also get into the group maybe after this meeting.
Yeah, if anyone have more questions later, just leave a message under the event page, so we can see them and somehow get back to you. For the future event, If you want to, I think Google Hangout can handle more people. I can't invite everybody join the Hangout and ask question, but I can certainly add as many as I can. Just let me know and give me your email address. I can add you in. Yep. Thank you very much, Chan and Tom. That's
Hey,
great
thank you.
talk. We learned a lot.
And also, thank you for the invitation, and thank you
Yeah, thank you
the
everyone.
audiences too for your time.
Have a good night.
Yeah, thank you.
Yeah, thank you,
Bye.
you too. Bye.